All right, so welcome to I think this is the third video for section 9.3. I'll do it in two videos, okay? So why don't you pause, copy this panel down, and then press play. All right, so in section 9.3, we're actually going to figure out how to find a line of best fit to fit data xi comma yi, all right? And we're going to call this the least squares regression line, right? And best is subjective. I mean, there's a lot of different ways we could measure best fit. Here's just one of them. We're going to say best is going to minimize the prediction errors. So we're going to figure out, well, what's the actual y value of the data and what's our predicted y value? What's the difference? Okay. And we're going to try and minimize those things. It's a bit of a lie. We're actually going to minimize the square of those errors, all summed together. If we minimize the square of the errors, we minimize the errors as well, we can show. Okay, so we're going to actually try and figure out the minimum sum of the squares of the errors, right? Okay, so we've got our data and data points, x1, y1 up through xn, yn. And I'd like to figure out values of a and b so that this linear function is really close to the actual data outputs y sub I for each x sub I. So I'm going to figure out the difference between the truth and my model, my linear model, square it, and sum it over all the data points. Okay, I'm going to call that function g. We know how to minimize using calculus. I'm going to take the partial derivatives of g with respect to a and b, set them equal to 0, and do a bunch of algebra and solve. And then I'm going to test that the critical points I find actually yield a minimum and not a maximum or a saddle point, if you remember from Math 200. Okay, so skipping all that details, because the details are left to the interested viewer. I get a value of b, which is the sum of these products, xi minus the average of the x's times yi minus the average of the y's, all over the sum of xi minus the average of the x's squared. Okay, so that's my value of b, which is the slope of my linear regression model. And then to get a, I'm going to take b, multiply it by the average of the x's, and then subtract from the average of the y's. So there's my a, there's my b, and this will be our linear regression model. We put a hat over the yi to say that's our predicted y value given the input x sub I. So there's my linear regression model. It's y sub I hat is my predictor or my fitted value, and we call this the least squares regression line, or least squares regression line of best fit. Okay, so why don't you pause? Oh, good, that's good. Why don't you pause, copy this stuff down, and then press play. All right, well, so we've got a way of calculating this a and this b given a data set. And there's some nice properties. First off, notice that we defined a to be the mean of y minus b times the mean of x for the data. And if I solve for y bar, I get a plus b times x bar. And that's exactly the linear regression model with x bar plugged in for x. That tells us that the point x bar comma y bar is a point on this line. So the least squares regression line of best fit always goes through the average of the x's and the average of the y's. And that's kind of pleasing. Okay. There's also another nice consequence. If we take all the predicted values of y from this linear model and average them out, we get the same exact average as the actual average of the y values. In other words, the average of my predicted values is equal to the average of the actual y values. And it's an easy proof. So yi hat is a plus b xi. So if I take the average of all those guys, I'm going to sum n copies of a. There they are. I'm going to drag that b out and sum up all the x's. There it is. I'll run the 1 over n through, just get an a, and then I get a b times this guy. And that guy is exactly x bar. And I know that a plus b x bar is equal to y bar from what we did above. Okay. So this least squares regression line of best fit has a couple of nice properties. It goes through x bar, y bar, and the average of our predicted y values exactly matches the average of our actual y values. It's not too shabby. Okay, so this next bit, which I think I'll stop in the video here on, first video here is just some notational simplification. All right. So rather than writing this sum the squares down, I'm going to say it's SSX. So this is the sum of the squares of the actual x values minus their mean. So it's sort of the variance from the mean of the x values. SSY is similar for the y's, and these stand for sum of squares for x, sum of squares for y, and then SSXY is the sum of xi minus x bar, yi minus y bar, all added together, okay? All right, well, if you remember or look back in your notes, the b value was the sum was this quantity, SSX, divided by this quantity, sorry. The b value was this quantity, which is SSXY, divided by this quantity, which was SSX. And if you remember from one of the previous videos for chapter 9, first or the second one, R is equal to, by definition, SSXY divided by the square root of SSX times the square root of SSY, okay? All right, that's the correlation coefficient. All right, well, what all that implies is, I can do a little bit of algebra here. I can run this SSX next to B and I get that guy. And SSXY, I can also run this square root next to R and get that guy. So SSXY is equal to either of these two things. And if I solve these two objects for B by dividing the SSX underneath, I get that. And you'll note that the square root of SSX on top cancels with one of the square roots of SSX downstairs, leaving me with this. So I have B is equal to R times the square root of SSY over the square root of SSX. And if I square both sides of that, I get B squared is equal to R squared SSY over SSX, okay? All right, so that's a nice thing to keep in mind. And this also implies that if I replace SSY and SSX with SY and SX, if you recall, that's the sample standard deviation, the equality still holds. And you might say, well, hold on, SX and SY have those 1 over n minus 1s underneath the square root. Yeah, they both do, so they would cancel, leaving us right back with those expressions in their place. So we also have B is equal to R times the sample standard deviation of Y over the sample standard deviation of X. Okay. All right, I'm going to pick up the next video with this idea on the next